Hello and welcome to Lecture 28, where we're going to talk about something called rotational dynamics. When you hear the word dynamics, you should think forces, and that's absolutely what is going on here. We're talking about forces, but we're talking about forces that create rotation, and as you've recently learned, forces that create rotation aren't forces anymore because they're forces multiplied by distance, and they're a vector, and they are called torque. So here, although it's still related to forces, dynamics means torques. Okay, so that's going to be what we're talking about. You might be like, well, I already know about torques. We had a section on torques. That was how to calculate torques. Now we're going to find out what we do with them. Okay, all right, so let's get into our key terms here. So you have moment of inertia, which is the missing piece of the puzzle. You'll see why. And then kind of a particular situation that is a dynamic situation. It's a situation that involves motion and torques, which is rolling. And it's not the only type we're going to look at, but it's one that deserves special attention. Okay, so what is the moment of inertia? Well, it's rotational mass. And in fact, sometimes I will call it rotational mass. Sometimes textbooks call it rotational mass, right? So it's like, kilograms is translational mass or translational inertia. Moment of inertia is rotational mass, okay? So the moment of inertia plays the same role as plain old inertia, but with torque and angular acceleration instead of force and acceleration, okay? So it's very much just a replacement for the for mass, right? And by the way, it's represented by the letter I. So essentially it's like M is becoming I, now that we've moved from translational systems to rotational systems, okay? So it is calculated from mass and the distribution of mass. And the common moments of inertia are given in tables. For example, the moment of inertia of a sphere is 2/5 mr squared. That's because they require quite a bit of calculus to actually derive, so often they're just stated as, oh, here's the moment of inertia, or they're just given numerically. It's not like with mass where you just either know it or you don't. With the moment of inertia, you have to actually know something about where that mass is located, so it requires a bit more work. And you see the theme there, right? Because forces, it's like you're just given a force, and maybe you need to know its angle, but you didn't have to have a whole lecture about how to calculate it. Torques, right, which are, after all, rotational force in a sense, we had to spend a whole section about how to calculate them and thinking about angles and what role they play. So everything about rotation is like translation, just more complicated, okay? And I'm not trying to scare you, but that is the reality of it. Everything requires an extra step, okay? So now what is rolling motion? Well, it's translation and rotation put together. Why have one when you can have both, okay? Obviously, a lot of things roll. It's a very, applicable type of situation. It applies to many, many situations. It's often driven by gravitational torque, right? A lot of rolling, if you think about rolling downhill in particular, all right? And that would be the gravitational torque acting relative to an object's center of mass, okay? And relative velocity is needed to understand rolling, right? You remember relative velocity? VAB equals VAC plus VCB, okay? So that's what we consider about rolling motion, because it really helps if we consider relative velocity to not have some misconceptions about rolling motion. And in fact, that's what I have the purpose of this figure here. Let's zoom in on it a bit. Okay, so here a good way of thinking about rolling motion is to think of it as pure rotation plus pure translation. All right, and that gives us rolling motion. So if you think about something that is rolling in place, so imagine that axle is fixed in place, that's pure rotation. I guess it would be in this direction, okay? That's just pure rotation. Now, pure translation is just the whole thing is moving, right? Okay, that makes sense. We've seen both. When you add them together, you get this. Notice, right, it's a little odd. That means that relative to the ground, the top is moving twice as fast as the center. The center is moving at, the standard rate relative to the ground. And then this point, which we call point P, isn't moving at all. Wait, what? What do you mean it's not moving? I mean, the whole thing is moving. But relative to the ground, it's not, okay? The contact point of a perfect rolling object, in this case called P, is not moving relative to the ground, all right? Now, this is fine, and this figure does a decent job, but let's refer back to the equation to make a little bit more sense of it. So let's consider the 2 points. We'll ignore the center. Let's focus on the more interesting ones. T for top and maybe P for point of contact. I don't know what they stand for, but T and P. T is clearly the top here, and then P is the bottom, which is also the point of contact with the ground. Okay, so now let's think about a relative velocity. We've got the velocity of a point relative to the center of mass. So that's P relative to com, okay? And then we've got the velocity of the com, the center of mass, relative to the ground, right? So P relative to com relative to the ground. So according to the relative velocity equation, the com should get squeezed out, and then we should just be left with a point relative to the ground, right? And indeed we do. Okay, so this definitely checks out. This must be true. And as long as we follow the vectors, we'll get the right answer. All right, well, the velocity of look at t first. The velocity of t relative to the center of mass is v, right? We can clearly see that, okay? Meanwhile, the velocity of the center of mass relative to the ground is v. We can clearly see that from our pure translation figure here, figure b, all right? And notice that's going to be the same for both of them. And that means that the velocity of point t relative to the ground is just 2v. Okay, that totally makes sense. It is moving twice as fast as the middle relative to the ground, or as the center of mass relative to the ground. Point t is twice as fast as com relative to the ground. Okay? Now what about p? Well, p has a velocity relative to the ground. Velocity, after all, has magnitude and direction, so it's negative v, right? Because of course it's moving in the negative direction. And then the com relative to the ground is still just v. That means that if we add them together, we get 0. So the velocity of point P relative to the ground is 0. It really is. It's not moving relative to the ground. It is actually fixed relative to the ground. And that's why when we talk about rolling motion, we actually use static friction for the contact, because there's no actual sliding going on. It's static friction. All right? This point P is at rest relative to the ground. Now, it then is going to lift up and be replaced by another point that is fixed relative to the ground. And in reality, there's not a single particle, an infinitesimally small particle in contact with the ground. There's some surface. And that means there must be sliding, because that surface then has to move away to have some other new surface replace it. But in a perfectly rigid object, it would be a single contact point, and it would not be sliding relative to the ground. It would be at rest relative to the ground. All right? That's rolling motion. And that's not to make it confusing. That's just explaining what it is. Okay? And by the way, I mean, and we're not saying that P isn't moving relative to something. It's moving at a magnitude of V relative to the center. It's still moving. It's just not moving relative to the ground. All right? So there we see that this shows that point P does not move relative to the ground. Okay? All right, so not much in the way of equations, which is nice, okay? Because we're going to see some pretty complicated examples. This is net torque. We've already seen that. Just the idea that if you are summing up torques, you just sum them up arithmetically like that. Now here's the cool thing. See this right here? Tau net equals I alpha. It's Newton's second law. It really is. It's F equals ma. But instead of F, it's tau for torque. Instead of m, it's I, because after all, it's rotational mass. And instead of a, it's alpha, which is angular acceleration. Right? Here are the labels. So it very much is in the form of F equals ma. All right? So if you're keeping track, how many times have we seen Newton's second law now? This is the third time. We saw Newton's second law, F equals ma. Then we saw F equals delta P over delta T. That was the momentum form of Newton's second law, the translation momentum form. And now we're seeing it in the torque form. Okay? And that's 3 out of 4. We got one last time. We're going to see Newton's second law coming up pretty soon. Okay, so let's go on to our practice. So I blocked it out into 3 types of problems. Fairly complex problems that involve using Newton's second law in rotational form for systems with blocks and pulleys with mass. All right, so that's pulleys with mass. And that's in contrast to every pulley we've seen up until this section, because we've always assumed our pulleys are massless. Okay, so that is going to be a difference. And I have an example that I think will really show it's a very similar looking problem, but now with that new added reality. Okay? And those are constant angular acceleration problems. Then we have type 2, which are problems that involve using Newton's second law in rotational form for solid objects pivoting about a single point, such as a physical pendulum. That's just like, imagine like a meter stick that you put up upright and you let it fall, okay? Or imagine a meter stick that you're holding at the top and you're letting it swing back and forth. Right? And that's in contrast to something called a simple pendulum, which is just a assumed massless string with like a bob, which is just all the mass at the bottom of the string. Right? Simple versus physical pendulums. Okay? But we'll actually talk about more pendulums in our oscillation chapter. All right, so that is non-constant angular acceleration. And then finally, type 3, complex problems involving Newton's second law in rotational form for, yep, you guessed it, rolling objects. Okay? So you can see here that it's no joke, they're all either fairly complex or something. There's no simple problems here. Okay? They all involve a lot of steps, but they are very procedural, and we are drawing on things that we're used to doing already, setting up sums of forces, doing some algebra, solving from unknowns, doing free body diagrams. That's all here, okay? Especially the free body diagrams. All right, so let's build on things and let's figure out these types of examples. All right, example 1. A hanging mass, got the mass, is attached to a pulley, radius 7 centimeters. The pulley is not assumed to be massless, okay? That's a big difference. as in previous chapters, and instead has a mass of significantly 2.75 kilograms. Okay, and that's true. A lot of pulleys can easily have a significant amount of mass. The only force acting on the system is the force of gravity. What is the acceleration of the mass as it falls downwards? Okay, because now if we had this system before, because this kind of looks like an Atwood's machine without the other mass. If we had this before, we would have approximated the acceleration of the mass as gravity. We would have had to have, because their only force acting on the mass would have been gravity, because there could have been no tension, because there would have been nothing. The pulley can't offer tension if it has no mass, right? And the string's assumed to be massless, so the block would have to fall at the acceleration of gravity. But that's not very realistic, is it? Because if the string is wrapped a few times around a pulley, then we know the pulley has to spin, right? Then it takes energy to get that pulley up and spinning, which means it takes force, which means it takes torque, which means that the block can't fall at the full acceleration of gravity. It has to fall slower, okay? And so hopefully that sounds realistic, and that's all we're doing here. We're just acknowledging that the pulley has mass, here represented by uppercase M, all right? So what is the acceleration of the mass as it falls? Let's do it, okay? So we're going to do something very similar, and I'll write a sum of forces and sum of torques. Now, at least the sum of forces is similar. We've already introduced torque, so we're just going to put them to use now. All right, so here we have F net in the y direction on little m. Okay, I'm zooming a bit on this because I'm writing small. So F net y on little m, all right? Well, let's think about my coordinates here. I have positive y pointing downwards and positive x to the right. So that means that we have, actually I don't. It kind of looks like I do here, but I'm actually defining positive y as up. So if you'll excuse a little bit, it doesn't matter at the end of the day, but it's important to be consistent. But here I am definitely causing positive or defining positive y as upwards, because we have tension as positive, and then we have mg, which would be this down here, as negative. And then also the acceleration of the block, a, is negative. So all the signs are consistent, but it is good to notice what direction I was assuming. Okay, all right, and there we go. We can see here that I'm defining it like that, positive y upwards. I ended up not using this coordinate system, I only used this one. Okay, and so then we have, the tension is just m times g minus a. Now this is exactly the kind of tension we'd see for any block that's accelerating, where there is, where it's accelerating downwards, right? And where that acceleration isn't free fall. We've seen this expression for tension many, many times, right? We've seen it in all those two blocks connected by a pulley. We would have seen this in the Atwood's machine, because the idea is that, once the tension goes to 0, then the acceleration goes to g, because the only way for the tension to be 0 is for a to be g, because then we'd have g minus g, okay? So hopefully that sounds familiar and makes sense, because we're building on it. Okay, so that's a tension, great. So here's the thing new. We're gonna do a sum of torques, all right? Now doesn't make sense to do torques on the block, because the block is not rotating. The only thing that is rotating is the pivot, around the pivot is the pulley. So it's the net torque relative to the pivot on big M, which is of course the pulley. Well, there's only a single torque acting on big M, on the pulley, which is just tension times the radius, just T times R, all right? And that means we're defining positive theta as this direction, as the counterclockwise direction, all right? Excellent. And then we'd be equal to I alpha, according to Newton's second law, right? Because this is the tau net, and here's the I alpha part, okay? And it's going to be positive alpha because it's going to rotate in the positive theta direction, right? The pulley's going to accelerate in the counterclockwise direction as the string gets unwound and as block M descends. Okay, so all I'm going to do is I'm going to replace T with the expression that I have for my net force equation, just substitution, and very important, because this you haven't seen for a little bit, but recall that A equals alpha times R, and specifically that's A tangential equals alpha times R, okay? We're going to use that quite a bit. And what that's telling us is that this component of translational acceleration is equal to angular acceleration times the radius. All right. Now you might be like, oh yeah, but what about centripetal acceleration? Well, centripetal acceleration doesn't show up in this problem because the block here is only moving in a direction that is tangential to the surface of the pulley. There is a centripetal acceleration, but it's not going to be relevant for calculating forces or accelerations. Okay. So at least translational accelerations. And so it doesn't show up. And so that really the acceleration now that's going to be the most important one is the tangential one. And I won't even draw the subscript, it's just A, And so that means what we're going to do is we're going to replace alpha, the angular acceleration of the pulley, with translational acceleration divided by the radius. Okay? Okay. So review our notes on angular quantities if you want to, if this doesn't sound familiar. Okay. So let's move on. All right, so at this point, it's just a matter of cleaning things up. I'm just going to take this expression. I'm going to cancel out r because we already have, basically on this side, I'm going to use something that isn't stated, but it should be, so I'm going to call attention to it. Is the moment of inertia here I? It's a pulley, and we're assuming the pulley is a cylinder. And so one of those tables that I mentioned a minute ago, tables for common moments of inertia, you have one in your book. I'm going to replace I with 1/2 mr squared. That's the moment of inertia of a cylinder. I tend to be more explicit about that, really clearly stating what it is. But here I'm not as much as I am in general, just for whatever reason. But this is the moment of inertia of a cylinder. Okay. So then as we clean things up, as I zoom in again, we clean things up and we got some nice cancellations. So then the left-hand side just becomes mg minus ma, and the right-hand side is just 1/2 ma. All right. So then as we go ahead and solve for a, do a bit more work, and there we go. So then our acceleration is just mg divided by m plus 1/2 m. And this looks kind of a lot like the acceleration we'd seen in Atwood's machine, which would be just mg divided by m total. But instead of m total, it's m plus the kind of the mass that matters. Because if after all, the moment of inertia is all about distribution of mass. So if the pulley was a different shape, this would not be 1/2 mr squared. It would be, say, 2/5, right? What if the pulley was a sphere? What if the pulley was a hoop, like a ring, instead of a solid cylinder? Well, we'd have different values here, okay? And so it very much matters, what the value is and how that affects the system, okay? In fact, the case where it's a hoop, this would actually be mr squared, in which case it would just be m plus m, because then all the mass essentially needs to be angularly accelerated. Okay, but anyway, so then we plug in our numbers and we get an acceleration of 5.11 meters per second squared. Okay. All right, move right on to part B. Is this acceleration constant? Yes, absolutely, because the translational acceleration is constant because it is dependent on constant masses. There's nothing changing in the system. There's nothing that is dependent on either angle or mass. And so we can clearly see that if A is constant, then so will alpha, because after all, alpha is just A times R. So both types of acceleration, the angular and translational, in this problem are constant. Okay, all right. And then part C, let's find the tension. Okay, so we're gonna go back for this expression of tension, and then we're just gonna substitute what we know for A. All right, so I just plug that in, clean things up a little bit. All right, just do some algebra. Okay, and you don't have to do as much. You literally could just plug in the value. I just wanted to get a nice kind of algebraic expression that's as clean as possible. But again, you could literally just plug in A right there, and you're done, because you know M, you know G, and now you know the numerical value of A. But I did all this work just to clean it up, and then I plug in the numbers, and there we go. I have 7.03 newtons. And the whole reason I would want to clean it up like this is so I can kind of clearly see what the dependencies are. What happens as M goes up or M goes up, how would that affect the tension? What's the trend, okay? And it's good if I want to make variations on a problem, I want to have it as clean as possible, okay? But there is our tension. That is a tension in the string that connects the block to the pulley. And lastly, what is the velocity of the mass after it has traveled a vertical distance of 25 centimeters? I actually forgot to give the value here because it previously was an entirely symbolic problem, but I want the problem to involve numbers for clarity. And so you can see here I wrote in by hand that the distance is 25 centimeters. Okay, that would be h. Okay, because somehow the block started up here, without pushing on the pulley. But this is h. Okay, it's just the height that the block falls. All right, so then for this one, we're just going to use kinematics, and we'll just take our acceleration, plug it in, and basically, this is just using one of the kinematic equations. Right, nothing special there. And there we go. It takes or its final velocity is going to be 1.6 seconds. All right, the velocity after it falls 25 centimeters, given this particular acceleration, which was dependent on the mass of the pulley as well as the mass of the block. Okay, and by the way, we could arrive at this value using conservation of energy, which is going to be the approach taken in the very next lecture after this one. All right, and that's conservation of energy, including rotational kinetic energy. All right, so let's do another problem. Again, kind of taking something we've seen before, a typical free body diagram, blocks, on a ramp connected by a pulley. But what are we going to do? What's new? We're going to give the pulley mass, right? Simple as that. And this time I'm not going to have the mass or have the moment of inertia come out of a table. I just state it numerically, and then I state the radius. Because when I state the moment of inertia, I have numerically like this, I have to also give the numerical radius because they're both going to be needed. Okay? But I did another slip up. I guess I had versions of this problem where I was thinking, I was going to have it be like a flat table, but then still connected by a pulley, something like this. But then I decided, I might as well make it a ramp for kind of comparison. And so I failed to give the angle. So here's the angle I should have given, 19.5 degrees. Okay, because that is, of course, necessary. I did, however, keep this problem a little bit simpler on this first pass, and I made it frictionless. Okay, so let's look at the forces then. So basically we care about the force of gravity acting on block 1. That's going to kind of drive the system, so to speak, right? Because as block 1 gets pulled down, everything else moves. In fact, as block 1 gets pulled down, the pulley starts spinning, this pulley with mass, a realistic pulley, and block 2 starts to get pulled up the ramp. Okay? All right, so what are the forces that matter? Well, we have a tension, okay? And that's the tension that is acting on this side of the pulley, and then we have a different tension on the other side of the pulley. Wait, no. We always had we've never done that before, but that's the new thing here. Now that the pulley has mass, the pulley has inertia, specifically a moment of inertia, rotational mass, that means that the tensions can't be the same on both ends, okay? They have to be different because essentially this tension there's a force, a tension force that's accelerating the pulley, and then there's some leftover force that's going to accelerate the block. But they can't be equal. F2 has to be smaller than FT1 has to be larger than FT2, okay? Because some of that tension got used up for the acceleration of the pulley because it has mass now, all right? So that's a big thing because we always just said, oh, well, there's one tension. Any problem like this. That was very much part of our problem-solving technique. And it still is if we want to have a massless pulley. But if we have a pulley with mass, we can no longer make that assumption. And that's tricky because it's something you're used to doing. So keep an eye out for it, okay? And since there's no friction, I don't even bother to show the normal force because the normal force would be the only thing that would really, contribute to the friction. And obviously there's no friction force as well, okay? So it's a simpler system in that sense. In other words, the only force other than tension that's acting in the x direction on M2 is a component of the gravitational force. Okay, so let's set up our sum of forces for block 2, block 1, and a sum of torques on the pulley. And unlike the example before, we're going to have 2 torques acting on the pulley rather than just 1, okay? All right, because there's the 2 tensions. All right, so write the sum of forces and torques, okay? So we have F net 2x, all right, which is just going to be the tension force, T2, because it acts on 2, hence subscript, and then a component of the gravitational force, the x component of the gravitational force. That's going to equal m2a, positive, because positive x is defined as up the slope. All right, so that's it for block 2, because I don't care about anything in the y direction on block 2. I drew its coordinate, but it's irrelevant to the problem. And then I care about the forces on block 1 in the y direction. Notice the y direction for block 1 is defined as straight down. And so then we have positive gravitational force, because it's in the positive y direction, minus the tension force, and that's going to equal m1a, because it's going to accelerate down, which is the positive y direction. And then finally, torque. I'm defining displacement, angular displacement, positive theta, as clockwise, which is not typical, but definitely a good choice here, because the pulley is going to turn clockwise. Basically, everything is moving, this way. And so to not have extra negatives, it makes sense to say, okay, well, hey, let's define positive theta as clockwise. That means that the torque created by Ft1 is going to be positive because it wants to turn the pulley in the clockwise direction. On the other hand, the torque created by Ft2 is negative, right? Because it wants to turn the pulley in the counterclockwise direction, which in this coordinate system is negative. And the pulley is going to accelerate in the positive theta direction, thus is equal to positive I alpha. All right, and this is again just Newton's second law in rotational form. All right, it's the new player for our setup here. Okay, because this is our setup. It's it's 2/3 of the battle, right? Now it's just algebra. Okay, so what do? Let's zoom out a bit. Okay, so what we're going to do is I'm going to go ahead and use both my force equations to solve for the 2 tensions, because that way, once I have the 2 tensions expressed in terms of just masses and accelerations, then I can substitute them into the torque equation, and then I can just find that acceleration. So essentially, I'm going to use these 2 equations to set up a substitution, substitute everything into the final equation, and then solve things out. Okay. So using F net 2x, I find that the Ft2 is m2 times g sine theta plus alpha. Makes sense that it's positive because the greater the acceleration, the greater tension acting on m2. Okay. And then using the sum of forces in the y direction on block 1. I'm going to then solve for for Ft1, the other tension. Okay, I know it's weird having 2 tensions, right? And this one is just going to be m times g minus a. This is what the total tension would have looked like before when there was just a single tension when the pulley was massless. I know I keep saying that, but we're used to doing it that way. Okay, and then I'll substitute both those tensions into the torque equation. That's all I've done here is I substituted Ft1 in its place and then Ft2 into its location. All right, and then look what I did. I replaced alpha with a over r. I told you that would come up a lot. Because now look at this. I have a single equation with how many unknowns? Just one, just A. All right? It shows up a lot of places, so I have to do some algebra here. So what I'm going to do is I'm going to take all my terms that have A and move them over to the right-hand side. So I'll distribute M1A and move it over here. And then I'll distribute negative M2A and move it over there. Okay? And so it's actually pretty simple because they're both negative, so they both become positive when I move them over to the right-hand side. So then I end up with I times A. So this is all multiplied, by the way. It's not as clear as it should be, but this is all multiplied by A. So I over R squared. Okay? Why R squared? Well, because I did one more thing. I divided everything by R. And if I divided everything by R, then this becomes R squared instead of just R. So I times R squared multiplied by A, M1 multiplied by A, M2 multiplied by A, equals everything that was left over on the left-hand side, because I'm writing everything on the left-hand side on the right, okay? And that's just G M1 minus M2 sine theta, okay? And that's just by cleaning up everything over here that didn't have an A in it. All right, and then I'm gonna go ahead and solve for A, because what I'm gonna do is I'm just gonna factor A out of these three terms that have an A in them, all right? And then divide this business by those three terms, so they show up in the denominator. And look what I get here. I get an equation that is really similar to what we would have seen for any type of frictionless, two blocks connected by a pulley over on a ramp equation, where it's the driving mass minus some component of the opposing mass, right? If this was an Atwood's machine, it would just be M1 minus M2. There'd be no angle at all. And then just divided by M total. But instead of M total, it's got this term that isn't quite like mass, still has the same units of mass, right? And you can tell it has the same units of mass because after all, the moment of inertia has units of kilogram meter squared. Well, you divide by radius squared, then you just got kilograms. So this is the mass, this is the mass, that's a mass. So this is like the effective mass of the pulley. Okay? All right, plug in our numbers, and there we go. That is the acceleration, because the one thing, even though the tensions are no longer shared by the two blocks, you know what is shared? The acceleration. The acceleration of M1 as it moves down, the acceleration of M2 as it moves up the slope, and the tangential acceleration of the surface of the pulley are all 0.416 meters per second squared. All right? So, similar but different. Okay? Okay, and on to our next example. This type of example represents one of those pivoting object type of problems. Okay, so let's read what's going on. We have a thin rod, right? It's a rod given here. We're given its mass. We're given its length. Okay? So that would be its entire length from the pivot. We're told that it has a center of mass that is 5/9 away up. So obviously its center of mass is not right in the middle, right? So maybe it's denser at one end, and it has a moment of inertia given by this formula here, 7/18, okay? ml squared. If the rod is free to rotate about its left end, so about that hinge, and is released from rest, so essentially we cut that string, and it's released from the position shown, 68 degrees with the vertical, what will be the angular acceleration of the rod at the moment it's released, okay? And imagine the cable snaps, as I said. Okay, so that's A. We're solving for acceleration. In a sense, there's less going on because we don't have to, like the previous example, consider less, two blocks on a pulley. So we just have one object, and we basically just need to consider the torques on that single object. Okay, so here we have it. Here we have the idea of the forces acting on the hinge at the pivot. And then we have one other force, which is the force of gravity. And the force of gravity always acts at one point only, and that point is the center of mass, which we know is 5/9 the distance up the rod. Okay. All right, so there we have it. Okay, so then we have torque net equals I alpha, just Newton's second law. Okay, now there's just a single torque. It's going to be gravity, and then it's going to be this expression here. Oh, excuse me. Okay, it's going to be 5/9 L times cosine theta. And where did that come from? Well, let's consider the angle here a bit. So we know that this angle right here, theta, is 22 degrees, which means that cosine of 22 degrees is the same as sine of 112 degrees. Why did I bring that up? Well, because if you actually think about the angle between the displacement vector and the force, so if we strictly think of the definition of torque, then torque is force times r times sine of the angle between the two. We'll call that phi. Well, if I imagine taking this force vector and putting it over here, and then having tail to tail my two vectors, my r vector and my force vector, then the angle between the two is this angle right here. That would be phi. And that angle is greater than 90 degrees, and it is 112. So taking sine of 112 is a totally valid way of doing it, but I think it makes more sense, and I've said this before, to take a component of the length. So if I just take this component, which is the perpendicular component of the displacement vector, and that's perpendicular to the force, then that's what I get. And that's the cosine component of theta, right? But of course, theta is not phi, okay? So again, this is just the perpendicular component of 5/9 L, which is the displacement vector, okay? And this is a throwback to the whole lecture where I really went over how do we calculate torque. I bring it up because it can be a sticking point in problems like this. Okay, so hopefully that idea makes sense. And then we're just going to set that equal to I alpha. I is given, and then we got alpha. We're going to go ahead and then solve for alpha because we're asked for the angular acceleration. So we just divide both sides by 7/18 ml squared. We have one L that cancels out right away. All right, and the M cancels out as well. All right, and the M cancels out once I rewrite FG as MG. See? Okay, and so there we go. I simplify things a bit more, and there's our final expression. Okay, and then I'm going to go ahead and find out what that is numerically, and it's 28.8 radians per second squared. That is the angular acceleration. I could very well ask for, and you could very well solve for, the translational acceleration of any point. You could say find the translational acceleration of the center of mass. So A com would just be alpha times 5/9 L. You could find the translational acceleration of the tip, in which case alpha tip would just be, or A tip would just be alpha times L. All right, so that's the idea. Obviously, you can go back and forth from rotational kinematics to translational kinematics using those key formulas to relate the two. But anyway, for angular acceleration, it's 28.8 radians per second squared. All right, and then part B I ask, is it constant? And no, it's not. And the reason it's not is because the angular acceleration, as well as the translational acceleration of any particular point along the rod, is non-constant because they are dependent on the angle. Look right there. In the very calculation of alpha that we did, the angle showed up. All right, that was not the case for the acceleration for the previous two examples. Okay, so a system like this has non-constant angular acceleration and translational acceleration. A system like pulleys has constant acceleration as well as constant angular acceleration. Okay, so do distinguish between the two. All right, let's do another one here. Okay, so this is a rolling problem. Okay, and there's a lot going on in this rolling problem. So I'm gonna, kind of go through the key steps, but try not to spend forever on it. A solid cylinder and a thin circular hoop are released from rest at the top of a ramp, and they're allowed to roll to the bottom. They both have the same mass, okay, and the same radius. Okay, well, okay, maybe they're the same then. And the ramp has an angle of 18.8 degrees, okay, above the ground, and a length of 40.6 centimeters. Okay, that allows us to calculate the height, right, if we need it. And by how many seconds does the cylinder beat the hoop? Why would the cylinder beat the hoop? Because the cylinder has a smaller moment of inertia than a hoop. Okay? So let's look at the picture, right? This is it. Here's the ramp, here's our known length, there's our known angle, and here's our two objects. This is the cylinder, this is the solid object, and that's the hoop, obviously. Okay? S for cylinder, H for hoop. All right? And those are just calling attention to the fact they have different moments of inertia. Otherwise, they're identical, remember? Same mass, same radius. Okay, so how do we set this up? Well, we want to think about the torque relative to the pivot. Well, what is the pivot? The pivot is the center of mass, okay? So if we consider the forces, I'm going to go down so I can show you something. Okay, so if we consider the forces, here are the forces relative to the pivot. Now, there's two ways to approach a rolling problem. You can choose the pivot as being the contact point, like in the key terms section, where that would be P. You can also choose the pivot to be the center of mass. You'll get the same answer in both cases, okay? Now, there's pros and cons to both. When you choose the pivot to be the center of mass, you can use the moment of inertia that comes right from a table of moment of inertias. For the sphere, it's just going to be 2/5 mr squared, and for the hoop, it's going to be mr squared, just 1 mr squared, okay? However, you then have to worry about the fact that you have the friction force is the only force that is creating a non-zero torque, because the normal force, it would be creating a zero torque since it has no angle relative to the moment arm, and the gravitational force will be creating a zero torque because it acts at the point that you chose as your pivot. And so your only force then that creates a torque is the friction force, which is okay if you know something about the friction, but if you don't know anything about the friction, then there's no reason to find anything about it. Now, you can, at any point, you could solve this problem and go back and find the friction that's necessary for the ball to roll, because the friction has to be there. The ball cannot roll without static friction. So you can actually calculate the necessary static friction for the ball to roll based on its mass and the angle, okay? But you can just avoid considering the friction in a problem like this where it wasn't asked for. But there is a drawback, and that drawback shows up right here. So I'll get to it. I'll kind of work up to why there's one extra consideration by choosing the contact point as the pivot, which in that case, of course, means that the friction force creates zero torque, and the only non-zero torque is that created by the gravitational force. All right, so here's our pivot, which is going to be P, as shown in the figure. The normal force creates zero torque. The friction force creates zero torque, okay? So the only torque that is created is that of the gravity. I'm calling positive theta counterclockwise. However, that means that the torque created by the gravitational force is negative, but likewise, the angular acceleration is negative, so the negatives cancel out, okay? So then I'm going to go ahead, all right, and I point out it's the center. And so then I'm going to go ahead and solve for alpha, which is then just going to be mgr, because there's my mg. The r was just the displacement, okay, from the center to the pivot, from the center of mass to the pivot, that's r, which is just the radius, okay? And then sine of 18.8 degrees. Well, 18.8 degrees was the angle of the ramp, and it's also this angle, just by basic geometry, okay? And then I divide by I. But what's the I? I is the moment of inertia. Is it the moment of inertia of a cylinder or a hoop? Not quite. It's, zoom in on it so you can see it, it's this expression right here, all right? Now this would be given in a problem like this, and I'd give you the moment of inertia. I would remind you, technically this is called the parallel axis theorem, which is not something that we cover in the class. It's a rather simple theorem that simply says you can move the moment of inertia from one point to another by taking the moment of inertia about the center of mass and then adding mass times the distance that you moved the pivot point. So since I moved the pivot from the center to a point in contact with the ground, I moved at a distance of 1 radius, okay? So that means that my new moment of inertia, because moment of inertia, like torque, depends on where you calculate it about, all right? So when you look at moments of inertia for common objects, that's assuming you calculated about the center. And sometimes that's stated, sometimes it's not stated and assumed, so beware. But that is always the case. Moment of inertia is dependent on the point about which it is calculated, okay? So in this case, the moment of inertia, for example, of the sphere is going to be the moment of inertia about the center of mass, which is 2 over 5 times mr squared that you'd find in the table, plus mr squared. Why? Because of this right here, which in terms of key words is called the parallel axis theorem. Okay? And that's the entire theorem, it's just that statement. Okay? So then, let's see. So then we're going to go ahead and calculate. Notice what I have here. This is alpha. I'm going to look at A, because that will give me the translational acceleration, which I care about, because after all, I'm going to compare the time it takes the two objects to roll down the ramp. That's very much a translational question. And so I don't, although it's interesting to know at what rate they're speeding up, because they are speeding up as they roll. It's the whole point of rolling downhill, right? But I care more about how fast their center of mass is moving. So if I'm going to go from the angular acceleration of the entire object to the translational acceleration of the center of mass, then I simply have to multiply angular acceleration by radius, okay? That's that same type of relationship we've seen again and again, okay? So then my translational acceleration of the sphere, okay, and specifically the translational acceleration of the sphere, well, let me say this way. The translational acceleration of the sphere's center of mass relative to the ground, okay, remember, is this expression right here. Now it simplifies so much because you got the m's cancel out, the r's completely cancel, right? Because there was an r squared in the numerator and the denominator, okay? Because of the extra r to go from a to alpha, or from alpha to a. All right, and so then we end up with this expression. It's just 5 over 7 times g times sine of theta. So it's just a fraction of g, okay? But it after all, should have the same units of g. It is, after all, in translational acceleration. Okay, good. We did it for the sphere. Now we're just going to do the same thing for the hoop, okay? So the same exact expression for the hoop. In this case, the pivot moment of inertia would be the moment of inertia of the hoop about its center, which is just mr squared, and then plus another mr squared because we moved the pivot point from the center to the contact point, okay? And so then we get 1/2 g sine theta for the hoop, okay? So check out those two translational accelerations. Which one's larger? Well, of course, the sphere. The sphere rolls faster. And there's an important idea there. The object with the smaller moment of inertia will always roll downhill faster. So the slowest thing that will roll downhill is the hoop, because the hoop has the greatest possible moment of inertia, because the ideal hoop has all of its mass distributed all the way around the edge. So its moment of inertia relative to its center is mr squared, which is the biggest possible moment of inertia there is, okay, for a particular value of m and r. Okay? And regardless, notice that translational acceleration is completely independent of m and r. I could have just left these numbers out. They don't matter. It literally does not matter how big the sphere is and how big the hoop is. And you might be like, wait, but of course a bigger hoop would get to the bottom faster. No, it would just accelerate really slowly because it's really big and has a lot of inertia. Sure, one turn would be much greater, so it wouldn't make as many turns, but it would still get to the bottom in the same amount of time. Okay? So the actual acceleration is independent of size and mass. Okay? But what is it dependent on? Shape, the distribution of mass. So interesting, so interesting. Okay? And in comparison, since we have these accelerations, what would be the acceleration of a block that's sliding down? Like just a frictionless block sliding down this ramp here. Well, in that case, it would just be g sine theta. So the block would be even faster, all right? The block would be twice as fast as the hoop, which is the slowest possible case, and at least in terms of shapes that don't have more mass distributed kind of out, shapes that truly roll. Because you could have like a yo-yo shape where there's extra mass that's like beyond the actual surface, like if there's like a notch or something and you have mass inside that notch. And so in cases like that, you can actually have something that's even slower than a hoop. But in terms of shapes that are actually contacting the ground on their outer edge, the hoop is the slowest. And it's twice as slow as the block. Okay? But even the sphere is slower than the block. Okay? The block's faster. Why is that? Well, as we talked about in the next section, it's because the block doesn't have to share energy with rotational kinetic energy. It can put all of the gravitational potential energy into kinetic translational energy rather than into kinetic rotational energy and kinetic translational energy, because rotating takes extra energy. Okay? All right. So kind of lots of ideas there. And now we're just going to use translational accelerations to find the time. But first, let's go off on one more tangent. Let's consider an idea here. Okay? So note, although present, the friction does no work. Okay? And again, you could solve for the static friction coefficient, but it's important to acknowledge that it actually doesn't do work, to bring it back to an idea of energy. All right? It does no work on objects that are rolling without slipping, which is pure rolling, which is the only type of rolling we cover in this class. All right? So note, the acceleration of the center of mass relative to the ground is equal to the tangential acceleration of the perimeter relative to the center of mass. And this is the same idea that was presented. And that's why we can do this equation right here. Okay? So if this seemed a little fishy, just going from, say, oh, well, translational acceleration is just alpha times r. The reason it works is because of the relative velocity equation, moving from one point to another and considering motion relative to the center, and then the center's motion relative to the ground, thus telling us that the center relative to the ground is the same as the motion of the perimeter relative to the center. Okay? And that's important because that does allow us to use this relationship, which certainly is a helpful one. Okay? So you can see here, there's a lot of ideas, although the calculation is not all that complicated. Okay? All right. So now let's go ahead and wrap this up because we have our two accelerations, so we can just go ahead and just use kinematics and finish this off. So we'll just find the time for the sphere to get to the bottom. That's simply going to be the square root of 2 times L over A. This just comes straight from one of the kinematic equations, right? If you don't remember which one, check it out. I bet you can figure it out fairly easily. All right, so plug in numbers, and there we find the time for the sphere to reach the bottom of the ramp of this particular length, 40.6 centimeters, at this particular angle is just over half a second, 0.599 seconds. Okay, for the hoop, it's 0.717. Not a big difference, but definitely slower. Right? Not a big difference for a couple of reasons, mainly because this isn't that long of a ramp. Okay? All right, so that means that the sphere arrives almost 0.2 of a second. Well, actually, no, just over 0.1 of a second before the hoop. 0.118 seconds before the hoop, which is just the difference between these two numbers. All right, so there you have it. Finding the time for them to arrive. And again, foreshadowing things to come, we can do the same problem and find out how fast they're both going at the bottom, and we can do it entirely with energy and not even worry about all this acceleration business, and that's actually quite a bit easier, as is always the case using energy. But if you are interested in time, energy is not going to tell you anything about time, ever, including for rotational systems, and so you would have to take this approach, consider torques, and thus angular accelerations, and then translational accelerations, okay? And again, we could have done it with friction. It would just been an extra step, but that would have allowed us to skip the parallel axis there. Okay, so we got one final example to wrap things up. This example would fall into kind of the category of the last two, where the setup's the hard part, the actual calculations are just a couple of lines. All right, so what's going on here? Well, we're pulling a cylinder up a step, okay? So a cylinder with a rotational mass, which is a standard cylinder rotational mass, 1/2 mr squared. So have you kind of recognized the common ones here? Hoop is mr squared, sphere is 2/5 mr squared, a cylinder is 1/2 mr squared. Those are the ones that come up a lot, okay? There's other things like a spherical shell, which is 3/5 mr squared, but so far, these are the common ones, okay? And then we've got the mass of our cylinder here, 12.7 kilograms. It's got a radius of 0.27. That's the radius right there, so 27 centimeters. All right, so it's standing vertically on a flat, frictionless floor, okay? No friction here because there's not rolling. A force F is applied at its center, okay? So that the cylinder will climb a step against which it rests. So we're essentially going to pull on it, and that's going to cause this whole cylinder to pivot up. So you can imagine like a minute later, it's pivoted up, and then eventually it's up over the step, all right? So the step has a height of 14 centimeters, so less than the radius, all right, kind of to scale in the picture. What value of the applied force is required so that the cylinder pivots about the edge of the step, so here's going to be our pivot point, with an angular acceleration of 20 radians per second squared, okay? Because we can make it pivot faster or slower, but we're specifying we want to pivot at this particular rate. Okay, well, let's see. Okay, so here is our pivot point. All right, there's our center of mass. The center of mass is the only location where gravity acts. Now, gravity is going to create a torque that's going to matter because we're going to choose this as our pivot, which means we're going to have two forces that create non-zero torques. All right, and then we have a displacement from the center of mass, which is the location where both the forces act, the gravitational force and the external pulling force, and the distance from that center of mass to the pivot point is r, okay? But of course, we're going to need some components, which we're going to calculate, all right? So if there's two steps, calculate the torque from F, the external pulling force, calculate the torque from the gravitational force on the cylinder. Then step 2, use Newton's second law in rotation form, okay? So this is a good picture here to kind of zoom in on the geometry that we're going to consider. Because we think about it, we want to consider components. And so we have a right triangle, I'll zoom in a tad. We have a right triangle here with one side of the triangle that's r minus h, and another side of the triangle that's r, okay? And a hypotenuse that is equal to, let's see, so, let's see. I'm just thinking about here because the hypotenuse obviously can't be the same as the side of the triangle. So this one, that's definitely r. Just trying to think about the, oh, right. So this value is r, it's a radius, but is not the side of the triangle, okay? Because obviously the side of the triangle, if it's a right triangle, would be slightly shorter than r, okay? So, but here I'm showing the radius, okay? All right. So then, what do we have? Then we have the torque from the pulling force is the pulling force times the displacement, r, times sine of phi. Because we care more about not the fact that this side of the triangle is slightly shorter than r. What we care about is the angle. And we're going to find the angle by just doing some trigonometry. So we have phi, which is this angle right here. This is going to give us the component of the displacement vector that is going to be perpendicular to the force, which is this component right here. So think of that as the component of r, right? If this is r, the displacement vector, which is also equal to big R in magnitude, being the radius, then the component that is perpendicular to the force, because here's the pulling force, the component that's perpendicular is that value right there, r sine phi, right? Phi being the angle between them, okay? Likewise, for the gravitational force, the angle between it, because the force goes down this way, and then the displacement is this way, so then the component that we care about that's perpendicular would be this one right here, which is also sine, but of a very different angle, it's sine of theta. Okay, now together, theta and phi will add up to 90 degrees, okay? So then we just have this expression. So I have, oh, there's one thing that's a little, it should say r minus h, the h got moved over, it should be right there, okay? I can fix that before I do the upload. All right, so I have tangent of phi is equals r minus h over r, which means then the phi is 42.9 degrees, okay? And again, that's just by doing the opposite over adjacent over here, right? So the two sides of the triangle are r minus h and r. To find phi, okay? All right, good. So 42.9 degrees, all right? And then theta then can easily be found as 47.1 degrees. Okay, so with those angles calculated out of the way, we can then just go on to set up our sum of torque equations. So because Newton's second law says net torque is I alpha, and then we got two torques. we're going to call positive, let's see, we'll call positive theta the counterclockwise direction, which means that the gravitational torque creates a positive, or the gravitational force creates a positive torque. And then the external pulling force, I know this always looks like friction, but it's uppercase F for external pulling force, as shown in the figure. That creates a negative torque because it wants to rotate it clockwise. All right, and that's just going to be equal to the moment of inertia, which is given in the problem, times alpha. All right, and it's going to rotate in the counterclockwise direction. Okay, and so then we'll go ahead and plug in our values and then solve for our force. And we find then that the force necessary is 83.6 newtons in order to get it to rotate in that direction at that particular angular acceleration. Okay, all right, so again, kind of a problem that involves rotation. Now this would be the angular acceleration at that particular moment in time, because just like the falling rod with its center that was not at the middle, that would have been example 3, this is dependent upon the angle. So the angular acceleration would be constantly changing, but we can definitely take a snapshot in time and find the force at that moment. Okay? All right. Well, thank you so much for watching this lecture. I hope it's been interesting. Rolling motion is a fun idea. All these applications of torque are fascinating at the very least, although they certainly do have a lot of steps. And I think maybe the thing that hopefully has really spoken to you the most is how we can take problems we've seen before, like the Atwood's machine and blocks connected over a pulley, and consider them more realistically, but still solve them, still do similar steps, and get an answer that makes sense. Okay? Well, again, thank you for watching.